Before we dive in, a quick but important note. The information in this presentation is for educational and informational purposes only. I am not a financial advisor or career counselor. This video is intended to provide a general overview of the commercial HVAC trade in the United States, but you should always do your own extensive research and consult with professionals before making any career or financial decisions. Picture this. It's the hottest day of the year in Dallas, a brutal 110 degrees in the shade. You're standing inside a massive, windowless building that hums with the power of a small city. This is a data center, the physical heart of the cloud, housing tens of thousands of computer servers that store our emails, our photos, our entire digital lives. And suddenly the hum stops. The air, once chilled to a precise 68 degrees, goes completely still. A wave of heat begins to build, and within seconds, red lights flash and alarms start screaming. Those servers, each one a tiny furnace, are generating so much heat that without constant massive-scale cooling, they will literally cook themselves to death in under 5 minutes. We're talking millions of dollars in hardware turning into molten plastic, and a catastrophic data loss for thousands of companies. Who gets the call? It's not an IT guy. It's not an engineer in a lab coat. The person who sprints into that building, the one person who can stop this multi-million-dollar meltdown, is a commercial HVAC technician. That high-stakes drama plays out in different ways all across America, every single day. In a hospital, where the air pressure and temperature in an operating room have to be perfect, or a patient's life is at risk. In a pharmaceutical lab, where a $100 million batch of a new vaccine will be ruined if the temperature fluctuates by half a degree. In a 100-story skyscraper, where the comfort of 5,000 office workers depends on a system so complex, it has its own dedicated power grid. These are the environments where commercial HVAC technicians work. They are the invisible engineers, the first responders for the buildings that run our economy. They are the guardians of our indoor world. So what do these people actually do? And why is it one of the most in-demand, high-paying skilled trades in the United States right now? That's exactly what we're going to uncover. If you're feeling stuck in a dead-end job, if you're looking for a career that challenges your mind and your hands, a career with real job security and a six-figure potential without a 4-year college degree, then this video series is your roadmap. We are going to break down piece by piece the reality of this profession, the money, the skills, the daily grind, and the exact steps to get started. And if you're just curious about the hidden world of technology and infrastructure that keeps our country running, you're about to get an all-access pass. First, let's get one thing straight. This is not about fixing the noisy air conditioner in your aunt's living room. That's residential HVAC. That's an important job, but what we're talking about is a completely different universe. It's the difference between being a family doctor and a specialized brain surgeon. A residential technician might work on a 5-ton unit that cools a 2,000 square foot house. A commercial technician works on a 5,000-ton chilled water system that cools a 2 million square foot convention center. The scale is monumental. The technology is infinitely more complex. And the stakes are astronomically higher. When a home AC unit breaks, someone is uncomfortable. When a commercial system at a supermarket distribution center fails, tens of thousands of dollars of food begins to spoil every single hour. The core of the job is problem-solving on a massive scale. These technicians are elite mechanical detectives. They don't just replace parts. They diagnose incredibly complex systems. They have to understand thermodynamics, fluid dynamics, advanced electronics, digital control systems, and high-voltage electricity. They read complex blueprints and wiring schematics that look like the secret plans for a spaceship. They have to be able to look at a chiller the size of a school bus, listen to the sounds it's making, analyze pressure and temperature readings from a dozen different points, and figure out why a tiny $50 sensor has failed, causing the entire system to shut down. And why is this job so valuable? 3 simple reasons: complexity, criticality, and the skills gap. We already talked about the complexity and the criticality. These systems are the lifeblood of modern infrastructure. But the third reason is the most important for anyone considering this as a career: the skills gap. The simple truth is, there are not enough qualified commercial technicians in the United States to do the work that needs to be done. The older generation of master technicians is retiring faster than the new generation is coming in. Meanwhile, buildings are getting smarter, systems are getting more complex and energy efficient, and the demand is exploding. It's a perfect storm of supply and demand, and it's driving wages and opportunities through the roof. This isn't a job that can be outsourced to another country. It can't be automated by a robot. You need a skilled human being on site with a brain and a set of tools to keep the world running. So let's lay the foundation. You'll see the acronym HVAC, or often HVAC-R. It stands for heating, ventilation, air conditioning, and refrigeration. Let's quickly break down what each of those means in the commercial world. Heating isn't just a gas furnace. We're talking about massive boiler rooms in the basements of hospitals, generating thousands of pounds of high-pressure steam that not only heats the building, but is also used for sterilization. We're talking about enormous rooftop units with complex heat exchangers and multi-stage gas burners. Ventilation is the lungs of the building. It's not just about blowing air around. It's about maintaining air quality for thousands of people. This involves huge air handling units with intricate filter banks that can remove microscopic particles. It means balancing air pressure between different zones, exhausting contaminants from labs or kitchens, and precisely controlling the amount of fresh, outside air being brought in to manage CO2 levels. It's a science in itself. Air conditioning is the big one. This is where you find the most impressive machinery. Forget the little condenser unit outside your house. Think bigger. Think about a row of 20 rooftop units on top of a Target or a Walmart, each one the size of a car. Think about a centrifugal chiller in a university basement, a multi-million-dollar marvel of engineering that uses thousands of gallons of water to cool an entire campus. These systems are so powerful their capacity is measured in tons, where 1 ton of cooling is the energy required to melt 1 ton of ice in 24 hours. A large commercial building can easily require thousands of tons of cooling. And finally, the R for refrigeration. This is a massive specialty within the trade. This is everything from the walk-in coolers and freezers at a restaurant or grocery store to the complex rack systems that keep an entire cold storage warehouse at 34 degrees. It even extends to industrial process chilling, where technicians maintain systems that cool plastics during manufacturing or keep sensitive equipment at a specific temperature. Heating, ventilation, air conditioning, and refrigeration. For pillars of a hidden industry, each one is a deep, complex field on its own. A commercial technician needs to be a master of all of them. They are the ultimate systems thinkers, the people who understand how all these massive, powerful, and critical pieces fit together to create a comfortable, safe, and functional environment. They are the reason our modern indoor world is even possible. So forget everything you thought you knew about fixing an AC unit. We're about to enter a world of high stakes, high tech, and high income problem solving. And it all starts with understanding the one fundamental principle that governs every single one of these massive systems, the very science that makes cooling and heating possible in the first place. It's called the refrigeration cycle, and you've experienced it 1,000 times without even thinking about it. Imagine holding an ice-cold can of soda on a blistering summer day. The can feels cold, right? But the real magic isn't the coldness of the can. It's the heat in your hand. That can is acting like a heat magnet, literally pulling the warmth out of your skin, leaving a cold sensation behind. You're not feeling the can's cold. You're feeling the absence of your own heat. That's it. That's the secret. HVAC at its core is not about creating cold. That's impossible. It's about moving heat. It's the science of taking heat from a place where you don't want it, like inside an office building, and moving it to a place where it doesn't matter, like the air outside. And the commercial HVAC technician? They are the masters of this invisible transfer of energy. They understand the language of heat. While you see a big metal box on a roof, they see a dynamic, high-pressure thermodynamic system constantly at war with the sun. This entire process, this heat-moving miracle, is accomplished by 4 key components, working in a perfect continuous loop. Think of them as the 4 main characters in a story that never ends. First, you have the compressor. This is the heart of the entire system. It's a powerful pump that takes a low-pressure, low-temperature gas, a special fluid called refrigerant, and squeezes it. It violently compresses it, which dramatically increases its pressure and, crucially, its temperature. This refrigerant gas is now superheated, much hotter than the outside air, and it's full of all the heat it just absorbed from inside the building. The compressor is the engine that drives everything. Next, this hot, high-pressure gas is shoved into the condenser. If the compressor is the heart, the condenser is the lungs. It's a giant coil of tubing, usually with massive fans blowing air across it. Remember that ice-cold soda can? The condenser is the opposite. It's now the hot can, and the outside air is the cool hand. Because the refrigerant is so much hotter than the air, it easily sheds its heat. As it releases all that unwanted heat into the atmosphere, it undergoes a phase change. It condenses from a hot gas back into a warm liquid, still under very high pressure. It has successfully dumped its thermal baggage. Third, we meet the metering device. This is the gatekeeper. It could be a tiny, precisely engineered valve or a long, thin copper tube. Its one and only job is to take that high-pressure liquid refrigerant and force it through a tiny opening. This causes a massive, instantaneous drop in pressure. It's like releasing the pressure on a can of spray paint. And just like that can feels cold when you use it, this sudden pressure drop makes the refrigerant become intensely cold, turning it into a frigid, atomized, low-pressure mist. Which brings us to our final character, the evaporator. This is the component that actually does the cooling inside the building. It's another coil just like the condenser, but this one is located in the airstream of the building's ductwork. The super-cold, low-pressure refrigerant mist flows through it. As the warm indoor air is blown across this freezing coil, the heat from the air gets sucked into the refrigerant, just like the heat from your hand got sucked into that soda can. The air, now stripped of its heat, becomes cold and is blown through the vents to cool the building. Meanwhile, the refrigerant, having absorbed all that heat, boils and evaporates back into a low-pressure gas. And where does that gas go? Right back to the beginning, to the inlet of the compressor, ready to be squeezed, heated, and sent on its journey all over again. Compress, condense, expand, evaporate, over and over thousands of times an hour. It's a closed loop, a perfect cycle. This is the fundamental physics that a commercial technician has mastered. It's not just a diagram in a textbook for them. It's a living, breathing process they can feel in the vibration of the pipes, hear in the hum of the compressor, and see in the readings on their gauges. They speak a language you've never heard of. Superheat and subcooling, enthalpy, saturated temperatures. They don't just look at a machine and guess what's wrong. They interrogate it. The call comes in. A 10-story office building's top floor is sweltering. The CEO's office is 85 degrees and climbing. The tech arrives, not with a giant wrench, but with a set of digital gauges and a multimeter. They hook into the system's service ports, and the machine starts talking to them in numbers, pressures, and temperatures. To the untrained eye, it's just a random data stream. To the technician, it's a story. The pressure on the low side is too low. The superheat is too high. Instantly, their mind flashes through the entire refrigeration cycle. They know that this combination of symptoms means the evaporator coil isn't absorbing enough heat. Why? Is it a blocked filter starving it of airflow? Is the refrigerant charge low because of a leak somewhere in hundreds of feet of copper piping? Is the metering device failing to deliver enough cold liquid? They are a detective, following clues written in the laws of thermodynamics. They start with the simplest explanation, airflow. They check the filters, they measure the fan motor's electrical draw. If that's not it, they move on. They use electronic leak detectors that sniff the air for microscopic traces of refrigerant, methodically scanning every joint, every valve, every inch of the massive system. They are hunting for a problem that could be the size of a pinhole, hidden somewhere in a machine the size of a truck. And we're not just talking about one box on a roof. A large commercial building like a hospital or a data center is a different beast entirely. We're talking about chilled water systems where a massive centralized chiller plant in the basement, a machine the size of a small bus, cools hundreds of gallons of water per minute. This chilled water is then pumped up 20 stories through a circulatory system of insulated pipes to air handlers on every floor, each one containing a coil that works just like an evaporator. The heat absorbed from the building is carried back down by the water to the chiller, which then uses its own massive refrigeration cycle to transfer that heat to another loop of water. That second loop gets pumped all the way up to the roof, to a cooling tower, a colossal structure designed to evaporate that water, releasing the building's heat into the atmosphere in giant plumes of steam. It is a symphony of machinery, a complex, interconnected ecosystem of pumps, motors, valves, and sensors, all orchestrated by a sophisticated building automation system. And the commercial HVAC technician is the conductor. They have to understand not just the refrigeration cycle, but hydraulics, advanced electronics, digital controls, and even water chemistry to keep the cooling tower from turning into a science experiment. The stakes are astronomical. If a data center's cooling fails, the servers that power our digital world, our banking, our social media, our entire economy, will overheat and shut down in minutes, costing millions of dollars. If a hospital's air conditioning goes out, sensitive operating rooms become unusable, and patient health is put at risk. This isn't about keeping office workers comfortable. It's about keeping the critical infrastructure of our society online and functional. So when you see that technician on the roof, they're not just fixing an air conditioner. They are a guardian of uptime. a high-tech problem solver fluent in the physical laws that govern our environment. They've moved beyond simply knowing the four parts of the cycle. They've developed an intuition and almost sixth sense for how these systems breathe, live, and die. And to do that, they rely on an arsenal of incredibly sophisticated tools that allow them to see the invisible and diagnose the impossible. So what's in this arsenal? Let's tear open the bag, pull back the curtain on the van, and look at the instruments that separate a parts changer from a master diagnostician. And no, we're not just talking about a bigger wrench and a fancier screwdriver. We're talking about tools that translate the secret language of machines into plain English. First, you have the absolute bedrock of any electrical diagnosis, the multimeter. But a commercial technician's multimeter is a different beast than the one in your garage drawer. It's a ruggedized, high-voltage, multifunction Swiss Army knife of electronics. It's not just checking for continuity or voltage. It's measuring capacitance to see if a motor start capacitor has the necessary kick to get a massive fan spinning. It's reading microamps to test a flame sensor. A tiny current that's the only thing telling a 10 million BTU furnace that yes, a fire is safely lit. And it doesn't need to shut down and plunge a building into freezing darkness. This single tool is the tech's link to the electrical soul of the machine. Without it, they're flying blind. But the real heart of the diagnostic process, the tool that looks like something out of a sci-fi movie, is the refrigerant manifold gauge set. Picture it: a block of solid brass with two large, color-coded dials, one blue, one red, and a web of hoses snaking from it. This isn't just a pressure gauge. It's the system's EKG. It's the lie detector. When a tech hooks this up, they are tapping directly into the veins and arteries of the refrigeration cycle. The blue gauge, the low side, tells the tech the pressure of the refrigerant as it's returning to the compressor, cold and in a gaseous state. This is the system's resting state, its inhale. The red gauge, the high side, shows the pressure of that same refrigerant after it's been compressed into a hot, high-pressure gas. This is its state of exertion, its exhale. A seasoned tech can look at the relationship between these two needles, the way they dance, the way they settle, and tell you almost everything. Is the blue needle too low? They call that being in a vacuum. It could mean a refrigerant leak or a critical blockage, like a clogged artery. Is the red needle too high? The system is overworking, struggling to shed heat. Maybe the giant condenser coils on the roof are caked in dirt and cottonwood seeds, suffocating the unit. Or maybe a condenser fan motor has given up the ghost. The gauges don't just give a number. They tell a story of struggle and strain. And today, these classic analog gauges are often replaced by digital manifolds. These are handheld supercomputers. They not only read pressures with pinpoint digital accuracy, but they have built-in thermometers that clamp onto the pipes. With this data, the device instantly calculates two of the most critical metrics in the entire HVAC universe: superheat and subcooling. Now, those words sound complicated, but the concept is beautifully simple. Superheat tells the technician how much extra heat the refrigerant has absorbed after it has already boiled into a gas. It's the ultimate proof that the evaporator coil inside is doing its job correctly. Subcooling is the opposite. It tells the tech how much the refrigerant has cooled down after it has already condensed back into a liquid. It's the proof that the condenser unit outside is working efficiently. Think of it like this: if the system had a fever or was suffering from hypothermia, these are the numbers that would prove it. A digital manifold takes the guesswork out of the diagnosis. It's the difference between a doctor guessing your temperature and using a precision thermometer. Next, let's talk about air. HVAC isn't just about temperature. It's about moving conditioned air. A technician needs to see that air to quantify it. For that, they use tools like an anemometer or a flow hood. An anemometer might look like a small handheld fan, but in reverse. It measures the speed of the air coming out of a vent. The tech can then use the vent's dimensions to calculate the CFM, the cubic feet per minute. This is the lifeblood of a building's comfort. Imagine a law office on the 20th floor complains that one entire wing is stuffy and hot, while the other is fine. The unit on the roof seems to be running perfectly. The tech goes into the stuffy offices, holds up their anemometer to a vent, and gets a reading of 50 CFM. Then they walk over to the comfortable wing, hold it up to an identical vent, and see 250 CFM. The problem isn't the air conditioner. The problem is a blockage in the building's lungs. A fire damper has tripped, a zone control motor has failed, a duct has collapsed. The anemometer made the invisible problem visible. But the most critical tools, the ones that elevate a technician from a comfort specialist to a guardian of safety, are the detectors. First, you have the electronic leak detector. This is a handheld sniffer that lets out a slow rhythmic beep. When it detects even a microscopic trace of refrigerant, the beeping goes wild, screaming at a high pitch. Finding a tiny pinhole leak in hundreds of feet of copper piping is like finding a single specific grain of sand on a beach. This tool turns the tech into a bloodhound. And then there's the combustion analyzer. This is without a doubt one of the most important tools in the entire truck. When a technician is working on any fuel-burning appliance, a gas furnace, a boiler, they are dealing with a controlled explosion. The combustion analyzer is a sophisticated device with the long probe that the tech inserts directly into the furnace's exhaust flue. It samples the outgoing gases and gives a precise digital readout of things like oxygen levels, stack temperature, and most importantly, carbon monoxide. Carbon monoxide, the silent killer. A properly functioning furnace produces almost none. But a furnace with a problem, a dirty burner, a cracked heat exchanger, can produce lethal amounts. The tech isn't just guessing. They're using this scientific instrument to see the chemical makeup of the fire itself. They might see a carbon monoxide reading of 400 parts per million, a number that is life-threatening. They will immediately shut the unit down, red tag it, and inform the building manager that they just prevented a potential tragedy. This one tool in the right hands literally saves lives every single year. Finally, you have the heavy machinery of the trade, the recovery machine and the vacuum pump. When a system has a major failure and needs to be opened up for surgery, you can't just let the refrigerant, a potent greenhouse gas, vent into the atmosphere. It's illegal and environmentally catastrophic. So the tech hooks up a recovery machine, a noisy, powerful pump that sucks every last ounce of refrigerant out of the system and stores it in a certified tank for recycling. Once the repair is made, the system can't just be refilled. It's now contaminated with air and worse, moisture. Moisture is the cancer of an HVAC system. It mixes with refrigerant and oil to create a corrosive acid that eats away at the system from the inside. To remove it, the tech deploys the vacuum pump. This isn't a shop vac. It's a scientific instrument designed to pull the system into a deep, deep vacuum, measured in microns. A single micron is 1/millionth of a meter of mercury. It is an incredibly small measurement of pressure. Pulling a system down to 500 microns or less boils away every last molecule of water, leaving the inside of the system clean, dry, and sterile. Only then, in that perfect void, can the system be recharged with pure, clean refrigerant, ready to run for another decade. So you see, the tool bag is not a collection of objects. It's an extension of the technician's senses. It allows them to see pressure, to feel temperature with 1/10 of a degree accuracy, to smell imperceptible gases, and to hear the subtle vibrations of a machine on the brink of failure. These tools transform a slab of metal and wires on a rooftop from a black box into a living, breathing entity with a story to tell. And the technician using this arsenal is the only one who can truly understand it. So what kind of story does a machine tell? It's rarely a happy one. It's usually a desperate plea for help, a cry that goes unheard by everyone except the technician. Imagine this. It's 2 p.m. on a blistering July afternoon in Phoenix, the kind of heat that makes the asphalt soft. Call comes in. It's not from a coffee shop with a warm thermostat. It's from the regional hub of a major financial institution. The voice on the other end is tight, panicked. Our main server room is at 92 degrees and it's climbing fast. We have 2 redundant 10-ton units up there and they're just blowing warm air. We're about 30 minutes from a system-wide thermal shutdown. A thermal shutdown, that's a polite way of saying millions of dollars in hardware starts to cook itself to death. Transaction data, customer information, the digital lifeblood of a massive company. All of it is on the line. This isn't about comfort anymore. This is about preventing a digital apocalypse. When the technician arrives, they don't just grab a wrench and run to the roof. They walk into that server room first. The sound hits you like a physical force. Not the gentle hum of an office, but the high-pitched, deafening scream of thousands of server fans spinning at maximum RPM. A desperate, futile attempt to cool the processors inside. The air is thick, and it smells of hot plastic and ozone. Anxious IT managers, people who live and breathe code and network architecture, are standing by helplessly, staring at a bank of monitors all flashing red. They've done everything they can. They've opened the doors, set up box fans. It's like using a squirt gun to fight a forest fire. They look at the technician not like a repairman but like a bomb disposal expert. This is where the story begins. The technician's first move is to plug their manifold gauges into the service ports on the indoor units. This is the equivalent of a doctor taking your blood pressure. The needles on the gauges tell a critical part of the story. The low side pressure is in a vacuum, the high side is through the roof. Instantly, the technician knows several things. It's not a simple thermostat issue. It's not just a dirty filter. The system is fighting itself. It's pulling so hard on the refrigerant that it's creating a vacuum, and it's pushing so hard on the other side that the pressure is dangerously high. The heart of the system is under extreme duress. Next, the multimeter with the clamp-on ammeter. They clamp it around the thick wires leading to the compressor. The reading on the screen is terrifying. The compressor, the massive pump that moves all that refrigerant, is drawing locked rotor amps. It's trying to start, but it can't. It's like trying to start your car with the engine completely seized. Every few seconds, you hear a deep thud and a hum, then a click as its own internal thermal overload protector shuts it down to prevent it from melting into a puddle of copper and steel. The machine is trying to kill itself to save itself. Now the technician has a clearer picture. It's a pressure problem. Something is preventing the flow of refrigerant. The story is getting darker. This isn't a simple fix. This is major surgery. The next chapter of this story is written on the roof. Under that relentless Phoenix sun, the rooftop units, called condenser units, are supposed to be rejecting all the heat pulled from the server room. But as the technician approaches, they notice something is wrong. One of the two giant fans on the top of the unit isn't spinning. It's just sitting there motionless, while the other one whirs furiously, fighting a losing battle. This is a massive clue. These fans are the lungs of the system. They pull the outside air across the condenser coils to cool the superheated refrigerant gas back into a liquid. If one fan is down, the unit loses half its ability to breathe. It can't exhale the heat. That heat backs up into the system, pressures skyrocket, and the compressor down in the server room is put under an impossible load until it shuts itself down. The entire catastrophic failure, the millions of dollars of hardware slowly baking 2 floors below, is all because of this one single fan motor. The technician confirms it with their multimeter. No voltage is going to the motor. They trace the wiring back to a small, unassuming component, the contactor. It's essentially a heavy-duty switch. Using an insulated screwdriver, they manually push the contactor in. Nothing. The motor doesn't even try to start. The story is now crystal clear. It's not the contactor, it's the motor itself. It's burned out. Dead. Now the race against time truly begins. The IT manager is calling every 10 minutes. Any update? The core temp on server rack 7 just hit 105. The technician has to work with a brutal combination of speed and precision. They kill the high voltage power at the disconnect. A heavy lever you pull with a satisfying clunk. They double and triple check with their meter to make sure it's dead. 480 volts doesn't give second chances. Then comes the grunt work. Unbolting the heavy protective grill. Carefully disconnecting the wiring. Loosening the set screw on the fan blade hub, which is almost always rested solid. It takes a breaker bar and all their body weight to get it to budge. They lift the heavy, dead motor out of its cradle, muscles straining in the oppressive heat. Sweat is pouring, stinging their eyes, but there's no time to stop. The new motor comes out of the truck. It's identical, but it represents hope. It slides into the mounting bracket. The wiring is carefully reconnected, each connection made tight and secure. The fan blade, a giant piece of precisely balanced metal, is slid back onto the new motor shaft and tightened down. The grill is bolted back on. This whole time, they're not just a mechanic. They're a surgeon, performing a transplant on a critical patient with the clock ticking. Finally, the moment of truth. They walk back to the disconnect. They take a deep breath and they throw the lever. Power is restored. They walk back to the unit, and the sound is beautiful. It's the sound of victory. Both fans are spinning in perfect unison, a powerful, steady roar, pulling a hurricane of air through the coils. The technician heads back inside, down to the server room. The change is already palpable. The high-pitched scream of the server fans is quieting down to a manageable hum. The blast of heat is gone, replaced by a steady, glorious flow of cold air pouring from the vents. The technician checks their gauges again. The pressures are perfect, settling right where they should be. The system is breathing again. The patient is stable. The IT manager comes over, a look of profound relief on his face. He puts a hand on the technician's shoulder. "I don't know how you did it, but you just saved our bacon. Big time. This isn't a made-up action movie scene. This is a Tuesday. And it's not just data centers. It's the operating rooms in a hospital, where a stable temperature and humidity are critical for patient safety. It's the pharmaceutical manufacturing plant where life-saving medicines have to be produced in a sterile, climate-controlled environment. It's the indoor vertical farm growing food for thousands of people, where a single day of system failure can wipe out an entire crop. The commercial HVAC technician is the unseen guardian of this critical infrastructure. They don't just fix air conditioners. They perform high-stakes triage on the complex mechanical systems that allow our modern world to function. They read the stories told by pressure, temperature, and voltage, and they rewrite the ending. They step into chaos, and with knowledge, tools, and sweat, they restore order. But how is that order maintained? How is it restored when it inevitably breaks? The work of a commercial HVAC technician isn't one single job. It's a constant cycle of three distinct, yet interconnected, roles: the guardian, the first responder, and the builder. Let's start with the guardian role, the one that prevents chaos before it can even begin. This is the world of preventative maintenance, or PMs. This is the unglamorous foundational work that keeps the modern world from grinding to a halt. Imagine a massive office tower, 100 stories high. On a Tuesday morning, a tech isn't there because something is broken. They're there to make sure nothing will break. They start on the roof, surrounded by air handling units the size of small buses. The city hums below, but up here it's a different kind of symphony: the rhythmic thrum of giant fans, the low growl of compressors. The tech's first act is to listen, not just with their ears but with their hands and their tools. They'll place a hand on the side of a motor, feeling for excessive vibration or heat that could signal a bearing about to fail. They'll listen for the telltale squeal or a new rattle that wasn't there last quarter. This is experience talking, a deep, instinctual knowledge of how a healthy machine is supposed to sound and feel. Then come the instruments. They pull out a multimeter, a device that lets them see the invisible world of electricity. They're checking the amperage draw on a compressor motor. Is it pulling more power than it should? That's a sign of strain, a cry for help from the heart of the system. Too high, and it could be on the verge of burning out, a repair that costs tens of thousands of dollars. They catch it now, and it might just be a simple capacitor replacement, a $50 part. Next, they'll break out the manifold gauges, that iconic array of colorful hoses and dials. They're tapping into the building's circulatory system, reading the pressure of the refrigerant. They're not just looking at numbers, they're interpreting a language. Is the suction pressure too low? Maybe there's a restriction somewhere, like a clogged artery. Is the head pressure too high? Perhaps the condenser coils, those giant radiators on the roof, are caked in dirt and pollen, unable to breathe and shed their heat into the atmosphere. So they get to work. They'll pull out massive filters, gray and choked with a season's worth of dust, and slide in fresh, clean ones. They'll meticulously tighten every electrical connection, because a loose wire is a fire hazard waiting to happen. They'll use powerful chemical sprays and high-pressure water to blast the grime off those condenser coils, restoring the machine's ability to exhale. They'll lubricate bearings, calibrate sensors, and document everything. Every reading, every action. This logbook is the building's medical chart, a history of its health that the next tech will rely on. This is the guardian's work. It's proactive, it's methodical, and 99% of the time, no one in the building even knows it's happening. They just know their office is comfortable. And that's the point. But sometimes, despite the best preventative care, things go wrong. That's when the tech transforms into the first responder. The call comes in. It's never, "Hey, can you swing by when you have a chance?" It's, "Our server room is at 95 degrees and climbing. We are minutes away from a total shutdown. Get here now." This is where the pressure is immense. A data center isn't just a room full of computers. It's the brain of a company. It holds the financial records, the customer data, the entire operational network. If it overheats and shuts down, the company isn't just losing comfort, they're losing money. Thousands, sometimes millions of dollars for every hour they are offline. The tech arrives on site, and the atmosphere is thick with panic. They walk into the server room, and it's like a blast furnace. The noise is deafening, a high-pitched scream from thousands of server fans running at full tilt, trying desperately to cool themselves. Red lights are blinking everywhere. The tech has to block all of that out. They have to silence the noise, ignore the anxious IT manager looking over their shoulder, and focus. Their first job is triage. What is the immediate problem? They get to the dedicated cooling unit for the room. It's running, but it's blowing warm air. This isn't a simple thermostat issue. This is major surgery. They get their gauges on the system. The pressures are all wrong. The story they're telling is one of catastrophic failure. They methodically move through the system, their mind a flowchart of possibilities. Is it electrical? They check the contactors, the breakers, the voltage. All good. Is it the refrigerant charge? They check the sight glass. It's full. They keep digging. They trace the lines, feeling for temperature differences. And then they find it. A solenoid valve on the liquid line is closed shut when it should be open. It's not getting the signal to open. Now the hunt goes deeper. Is the valve itself bad? Or is it the controller that's supposed to be telling it what to do? They bypass the controller, manually sending a 24-volt signal to the valve. Nothing. The coil is dead. It's a small, relatively inexpensive part, but it has brought a multi-million-dollar operation to its knees. Now comes the logistical challenge. Do they have the specific part on their truck? Every good service tech's truck is a rolling warehouse, but you can't carry everything. Quick check. No luck. They get on the phone with the supply house. Do you have a Danfoss EVR6 solenoid coil in stock? Yes. How late are you open? They race across town, get the part, and race back. They sweat in the oppressive heat of the server room as they carefully replace the faulty coil, their hands moving with a practiced efficiency. They restore power, the valve clicks open, and cool refrigerant begins to flow once more. Within minutes, the air coming out of the unit is ice cold. The temperature in the room starts to drop. The screaming fans begin to quiet down. The crisis is averted. The first responder has stabilized the patient. Finally, there is the role of the builder. This is the world of installation and retrofitting. This isn't about fixing what's broken. It's about creating something new. A company is building a new headquarters, or a historic hospital is upgrading its ancient, inefficient system. The tech is now part of a massive, coordinated effort with electricians, plumbers, and ironworkers. They're working from a set of complex blueprints, a roadmap of pipes, ducts, and wires. This is heavy physical work. They might be on a scissor lift 50 feet in the air, rigging a 2-ton rooftop unit into place with a crane. Every hand signal has to be precise. A few inches off, and the unit won't line up with the roof curb, compromising the building's waterproof seal. Inside, they're running hundreds of feet of copper line sets, using a torch to braze the joints together. This is an art form. The flame has to be just right, the temperature perfect. A bad joint, a tiny pinhole leak, and the entire system's charge of expensive refrigerant could bleed out, wasting thousands of dollars and damaging the environment. They pressurize the lines with nitrogen and watch the gauges for hours, sometimes days, to ensure their work is absolutely perfect. They're wrestling with massive sections of sheet metal ductwork, fitting them together like a giant, heavy jigsaw puzzle, sealing every seam to ensure that the precious conditioned air makes it to its destination without leaking into a ceiling cavity. In a retrofit, the challenge is even greater. They're surgeons, carefully cutting into an existing building to integrate a new modern system without damaging the structure. They're problem solvers, figuring out how to run a new duct through a space that's already crowded with a century's worth of pipes and wires. This is the birth of a building's lungs and its circulatory system. It's loud, it's dirty, and it's demanding. But when it's done, when they finally start the system up for the first time, there's a unique satisfaction. They feel the rush of cool air, hear the whisper-quiet hum of a perfectly balanced system, and see a complex set of plans and materials come to life. They haven't just restored order. They've created it from scratch. Guardian, first responder, builder. 3 roles, 1 technician. Each requires a completely different mindset, a different set of skills, and a different kind of strength. So let's talk about that strength. Because it's not the kind you measure in the gym. It's forged in the crucible of chaos, under the immense pressure of a world that cannot, will not stop. Let's start with the most obvious kind, the physical. This isn't an office job. There's no ergonomic chair. Your office is a screaming boiler room hot enough to bake bread, or a windswept rooftop in the dead of January, with an Arctic wind that cuts right through your layers and steals the dexterity from your fingers. It's crawling through dusty, forgotten spaces smaller than a coffin, your world illuminated only by the beam of your headlamp, with spiders and century-old dust as your only companions. It's hoisting a 50-pound compressor motor up 3 flights of stairs because the elevator is out, the very elevator you might be there to get cooling for. It's the raw brute force of breaking loose a rusted-on bolt that hasn't moved since the Reagan administration. Your muscles screaming in protest, knuckles bleeding, sweat stinging your eyes. It's the constant grinding wear and tear on the body. Knees ache from kneeling on concrete. Back strain from awkward angles. Hands become a roadmap of scars, calluses, and burns. This is a visceral, full-contact profession. You are physically wrestling with the built environment, imposing your will on stubborn, heavy, and often dangerous machinery. But that physical strength, as demanding as it is the entry fee. It's the baseline. The real work, the work that separates a parts changer from a master technician, happens between the ears. This is the mental strength, the intellectual horsepower. Imagine you're a detective arriving at the most bizarre crime scene. The victim is a 200-ton centrifugal chiller, the heart of a massive skyscraper. It's dead, silent, and thousands of people are slowly beginning to cook in their offices on the 40th floor. The 911 call has been made, and you are the one who answered. There are no witnesses. The machine can't tell you what happened. All you have are clues. A pressure reading here, a temperature differential there, an amperage draw that doesn't quite make sense. The building's management is breathing down your neck. Every minute that ticks by, the temperature in the building climbs, and the cost of the downtime skyrockets. This isn't about following a simple flowchart. The flowchart ran out of ideas 5 steps ago. This is about understanding a symphony of interconnected systems. You have to be a physicist, understanding the laws of thermodynamics and the psychrometric chart, that arcane map of air, heat, and moisture. You have to be a chemist, understanding refrigerant properties, oil compatibility, and water treatment. You have to be a master electrician, tracing complex 3-phase power circuits, diagnosing variable frequency drives, and understanding control logic that would make a software engineer's head spin. You have to be a plumber, a pipe fitter, and a computer programmer all at the same time. The system is giving you contradictory information. The sensor on the chilled water line says the water is cold, but the sensor on the return line says it's barely changed temperature. Is the first sensor lying? Is the second one broken? Or is there a flow problem? Is the pump running? The gauges say yes. But is it actually moving water? Or is the impeller sheared off its shaft, just spinning uselessly in the volute? You can't see it. You have to deduce it. You put your hand on the pipe. You feel for the subtle vibration, the telltale hum of moving water. You listen. You close your eyes and listen to the pitch of the compressor. A master technician can hear the difference between a healthy machine and one whose bearings are about to self-destruct. They develop a sixth sense for this work. It's an intuition born from thousands of hours of observation, of seeing every possible way a machine can fail. They see the invisible world. They see the airflow moving through a duct system. They see the heat being absorbed by the refrigerant, changing its state from a liquid to a gas. They see the pressure differentials that are the lifeblood of the entire system. They're not just looking at a machine, they are visualizing a dynamic living process. So the technician or detective suspects a flow problem. He bypasses a control valve, and suddenly the pressure differential changes. Aha, a clue. The problem isn't the massive chiller. It's a small, unassuming actuator on a valve halfway across the building that has failed in the closed position, effectively strangling the entire system. No manual, no diagnostic code would ever tell you that. It required a holistic understanding of the entire building as one giant organism. It required the mental fortitude to stay calm, to think logically and systematically while the world is screaming at you to just do something. This is the chess match. You're playing against the laws of physics, and the machine will exploit any weakness in your knowledge, any flaw in your logic. You make one wrong move, misdiagnose one component, and you could not only fail to fix the problem but create a much, much bigger one. Catastrophic one. You could blow a compressor, costing tens of thousands of dollars, or worse, trigger a refrigerant leak that endangers everyone in the mechanical room. And to win this chess match, they carry an arsenal of tools that goes far beyond wrenches and screwdrivers. They wield digital multimeters that can diagnose the most intricate electrical faults. They use combustion analyzers that sniff the exhaust of a boiler, measuring its chemical makeup with scientific precision to maximize efficiency and ensure safety. They carry digital manometer sets with wireless probes to measure tiny fluctuations in air and gas pressure. They use ultrasonic leak detectors that can hear the high-frequency hiss of a refrigerant leak that is completely silent to the human ear. And one of the most powerful weapons in their arsenal, the thermal imaging camera. This device allows them to literally see heat, a hot circuit breaker, an overheating motor bearing, a lack of insulation in a wall. It all becomes visible, painting a picture of the invisible world of energy they operate in. They are tech wizards, armed with devices that give them superpowers of perception. But even with all this technology, the most important tool is still the one they were born with: the human brain honed by experience into a razor-sharp diagnostic weapon. It's this combination of brutal physical work and intense intellectual rigor that makes the role so unique. They are both the surgeon and the soldier, operating with precision in a war zone of mechanical failure. They have the strength to move the machine and the intellect to understand its soul. But there's a third kind of strength, one that isn't physical or mental. It's the strength to carry the weight of what's truly at stake. This is the strength that separates a mechanic from a guardian. It's the emotional fortitude to stand in a room where the stakes are measured not in dollars, but in human lives, and to see not a tangled mess of wires and pipes, but a lifeline. Imagine a hospital. Not the waiting room or the cafeteria, but the surgical wing. A place of sterile precision where the air itself is a tool. It's filtered, pressurized, and chilled to an exact temperature and humidity. It prevents infection. It keeps surgeons focused and sensitive equipment from overheating. Now imagine the massive chiller plant on the roof. The heart of this intricate system suddenly has a catastrophic failure. The call that comes in isn't, the AC is out. The call is a quiet, urgent panic. It's a facilities director whose voice is tight with dread. He's not thinking about comfort. He's thinking about the open heart surgery in R3, the neurosurgery in R5, the transplant team prepping in R7. He's thinking about the fact that in 20 minutes, conditions in those rooms will become unsafe to continue. Procedures will have to be aborted. Lives will be put at risk. The technician who arrives on that roof isn't just there to fix a machine. They are the last line of defense. They are stepping into a pressure cooker where every single person, from the hospital administrator to the lead surgeon, is depending on them. They can't afford to guess. They can't afford to be wrong. They have to diagnose a multi-ton, million-dollar piece of equipment under a ticking clock that echoes with the beeps of heart monitors down below. They have to look at a schematic that resembles a city map and instantly see the one tiny capillary that's causing the entire system to hemorrhage. This isn't about turning a wrench. It's about performing a kind of industrial surgery to save the surgeries happening downstairs. The weight of that responsibility is immense. It would crush a lot of people. But a commercial HVAC technician learns to carry it. They have to. Or picture this, a data center. A vast, windowless building humming with a terrifying amount of power. Inside are rows upon rows of black cabinets, the silent, blinking brains of our modern world. Your bank records, your medical files, the logistics for the entire country's supply chain, the very fabric of the internet, it all lives here. These servers generate an incredible amount of heat. Without constant, massive-scale cooling, they would literally melt themselves into useless slag in minutes. Each cabinet is a furnace, and the entire building is a volcano on the verge of eruption. The HVAC system here isn't for comfort. It is the life support for our digital civilization. When a CRAC unit, a computer room air conditioner, goes down, alarms don't just sound. They scream. Red lights flash. The temperature in that hot aisle begins to climb 1 degree every few seconds. Automated systems start throttling server performance to prevent a meltdown. The company that owns the data center is now losing, potentially, hundreds of thousands of dollars with every passing minute. A technician is dispatched. They walk into a symphony of screaming alarms and the frantic energy of IT managers who see their careers flashing before their eyes. The tech has to navigate this chaos, enter a hot aisle that is rapidly becoming an oven, and work on a system that is inextricably linked to a multi-million-dollar network of electronics. A single mistake, a drip of condensation in the wrong place, an accidental power surge, could fry a server rack worth more than a house. They are working on the knife's edge of disaster. They have to know the thermodynamics, the electrical theory, the refrigerant cycles, but they also have to have the nerve to stay calm when the digital world is holding its breath. They are the paramedics of the information age, arriving on scene to a technological heart attack. That's the weight. It's the silent, unspoken contract they have with society. We will keep your hospitals safe. We will keep your data secure. We will keep your food from spoiling, your pharmaceuticals stable, your manufacturing processes running. This responsibility extends far beyond these dramatic examples. Think of a 100,000 square foot grocery distribution warehouse. The refrigeration system fails on a hot July day. Suddenly, millions of dollars of fresh produce, meat, and dairy are at risk of spoiling. This isn't just a financial loss for one company. It's a potential disruption for the food supply of an entire region. The technician who gets that call is fighting against time and temperature to save a literal mountain of food that thousands of families are depending on. Think of an elementary school in North Dakota in the dead of January. The boiler system that provides heat to the building goes down overnight. The temperature is 20 below zero. If that system isn't fixed before dawn, school is canceled. For some kids, that means missing their only guaranteed warm meal of the day. The technician who drives through a blizzard and works in a freezing boiler room isn't just fixing a heater. They're ensuring a child has a safe, warm place to learn and eat. This is the hidden layer of the job. It's the purpose that fuels them through the brutal hours, the complex problems, and the immense pressure. They don't just see the equipment. They see the context. They understand that the machine they are working on is a critical link in a chain that connects to people's lives, their safety, and their well-being. They have to be strong enough to lift a compressor, smart enough to diagnose a circuit board, and emotionally resilient enough to handle the fact that their work on any given day could be the only thing standing between a normal Tuesday and a full-blown crisis. This is the third strength, the strength of consequence. It's the understanding that you aren't just maintaining a machine. You are maintaining the quiet, humming, climate-controlled foundation of modern life itself. And in this world of invisible infrastructure, they are the indispensable unseen guardians. But to be a guardian in the 21st century, you need more than just courage and a strong back. You need an arsenal of technology so advanced, it's changing the very nature of the trade, turning wrenches into wands and diagnostics into a digital art form. Let's start with the basics, which are anything but basic anymore. Gone are the days of squinting at a wobbly needle on an analog gauge, trying to guess a pressure reading. Today's technician pulls out a digital manifold. This isn't just a pressure gauge. It's a diagnostic computer that fits in the palm of their hand. It measures pressures and temperatures with surgical precision, but its real magic is what it does with that data. It instantly calculates the system's vital signs, things called superheat and subcooling, which are like the blood pressure and heart rate of the refrigeration cycle. What once took multiple tools, a notepad, a calculator, and 5 minutes of frantic math, now happens in a fraction of a second displayed on a backlit screen. And it gets better. Many of these devices are now wireless. Imagine a technician working on a massive rooftop unit, the size of a small bus. In the old days, they'd hook up long, cumbersome hoses, run them back to their gauges, take a reading, then walk all the way back to the unit to make an adjustment, then walk back to the gauges to see the effect. Back and forth under a blazing sun. It was inefficient and exhausting. Today they attach small wireless smart probes directly to the pipes. These probes beam the live data in real time straight to a tablet or smartphone. The technician can stand anywhere, in the shade, right next to the component they're adjusting, and see the immediate impact of their work. They can balance an entire system, fine-tuning airflow and refrigerant charge across dozens of zones, all while looking at a single screen that shows them the entire building's circulatory system at a glance. They are no longer just mechanics. They are conductors of a complex thermal orchestra, ensuring every instrument plays in perfect harmony. But what about the problems you can't see? The ones hidden behind walls, buried in ceilings, or deep within the guts of a machine. This is where the technician's arsenal gets truly futuristic. This is where they gain superpowers. Enter the thermal imaging camera. This device doesn't see light. It sees heat. It translates the invisible world of thermal energy into a vibrant, color-coded image. A hot spot shows up as bright yellow or red, a cold spot as a deep blue or purple. To a commercial HVAC technician, this is nothing short of X-ray vision. Consider a sprawling office building where employees in one section are complaining of being cold, but the system seems to be running perfectly. The old-school approach? Start tearing into ceiling tiles, a messy, time-consuming game of hide-and-seek, searching for a leak in a vast network of ducts. The modern technician simply pulls out their thermal camera and scans the ceiling. Suddenly, on their screen, they see it. A long, dark blue streak cutting across the tiles. It's a river of cold air, escaping from a disconnected duct joint hidden from view. A problem that could have taken half a day of destructive searching is pinpointed in less than 30 seconds. They use it to find failing motor bearings glowing red with friction before they seize up. They spot refrigerant restrictions that show up as an abrupt, icy blue blockage in a copper line. They can even see where a building is losing a fortune in energy through poor insulation. They are literally seeing the invisible, turning abstract problems into concrete, visual evidence. And the exploration of the unseen doesn't stop there. What if the problem is inside the machine itself? A cracked heat exchanger in a furnace, for example, is an incredibly dangerous situation. It can leak deadly carbon monoxide into the building's air supply. The traditional method of inspection often required a complete, labor-intensive teardown of the unit. It was like performing open heart surgery just to see if there was a problem. Now the technician deploys a borescope. This is a tiny high-definition camera on the end of a long flexible cable. It's the same technology surgeons use for minimally invasive procedures. The technician can snake this camera deep into the furnace, navigating the tight, dark passages of the heat exchanger, watching the live feed on their screen. They can inspect every weld, every surface, every corner for the slightest sign of a crack or fatigue, without unbolting a single major component. They can diagnose a life-threatening condition with the precision of a surgeon, saving the client thousands of dollars in labor and preventing a potential tragedy. But perhaps the most critical piece of technology, the one that separates the professional from the amateur, is the combustion analyzer. When a technician is working on any fuel-burning appliance like a gas furnace or a boiler, they are dealing with a controlled fire. The goal is a perfect, clean burn, maximum efficiency, and minimum harmful byproducts. The old way was to eyeball the flame. Is it blue? Is it steady? It was more art than science, and it was dangerously imprecise. Today's technician inserts the probe of a combustion analyzer directly into the exhaust flue. This device is a portable emissions testing station. It sniffs the exhaust gases and gives a precise, digital readout of things like carbon monoxide levels, oxygen, and carbon dioxide. It tells the technician exactly how efficiently and, more importantly, how safely the furnace is operating. With this data, they can make micro adjustments to the gas pressure and air mixture, tuning the machine like a high-performance engine. They can dial it into a state of perfect combustion, squeezing every last bit of energy from the fuel, and ensuring the deadly, odorless carbon monoxide gas is at a safe, near-zero level. This tool isn't just about efficiency. It's a guardian. It's the piece of technology that allows a technician to walk away from a job knowing, with scientific certainty, that the people inside that building are safe. This fusion of digital precision, advanced imaging, and data analysis culminates in the ultimate technological challenge, the Building Automation System, or BAS. This is the central nervous system, the digital brain of a modern commercial building. It's a complex network of sensors, controllers, and software that monitors and commands everything: the chillers, the boilers, the air handlers, the dampers, the lighting, even the security systems. The commercial HVAC technician of today is no longer just a hardware specialist. They must be a software specialist too. They plug their laptop directly into the building's brain. They navigate complex graphical interfaces, read lines of code, and analyze trend logs that track hundreds of data points per minute. They can see the entire history of a building's climate, pinpointing patterns and anomalies that would be impossible to detect otherwise. A recurring pressure drop at 3 p.m. every Tuesday? The BAS log will show it. A valve that's slow to respond? The BAS will flag it. The technician can even diagnose and sometimes fix problems remotely, logging into the building system from their office miles away. They are becoming data analysts, network troubleshooters, and systems integrators. The wrench is still there, but it's now guided by a torrent of data flowing from a digital world. This is the new frontier. It's a place where blue-collar grit meets white-collar intellect, where the hum of a fan motor is just as important as the flicker of a cursor on a screen. And yet, for all this incredible technology, for all the sensors and software, the single most important tool in their arsenal remains the one that can't be bought, programmed, or charged. It's the 3 pounds of gray matter between their ears. It's experience. It's intuition. It's the almost supernatural ability to connect seemingly unrelated dots that a computer, for all its processing power, would simply miss. This is where the technician transcends the role of a mechanic and becomes a detective. Let me tell you a story, a real-world scenario that plays out in different forms every single day. Picture a brand new, cutting-edge corporate headquarters in Austin, Texas. A glass and steel monument to a billion-dollar tech company. Inside, everything is automated, a symphony of sensors and servers. But on the 7th floor, the executive wing, there's a ghost. Every few days, in the middle of the afternoon, the air conditioning dies. Not the whole building, just that floor. The temperature climbs, multi-million-dollar deals are discussed in sweltering boardrooms, and the CEO is furious. The building's own facilities team is stumped. The state-of-the-art building automation system, the BAS, logs a generic fault on a VAV box, a variable air volume unit, but it offers no reason. They replace the box. The ghost returns. They replace the controller. The ghost returns. They update the software, they check the network, they run diagnostics until the servers hum with the effort. Nothing. The problem is intermittent, maddeningly random, and it's making the most powerful people in the company look incompetent. So they make the call. They bring in a specialist, a senior technician from an outside firm. A guy in his late 50s with calloused hands and a face that's seen 1,000 mechanical rooms. He doesn't rush to plug in his laptop. He doesn't immediately pull up schematics. His first move is to walk the floor. He feels the air on his skin. He stands by the massive floor-to-ceiling windows and looks out. He listens. He closes his eyes and just listens. To the hum of the lights, the whisper of the diffusers, the distant thrum of the air handlers. He talks to the executive assistants. When does it happen? Is it always at the same time? What's the weather like when it goes out? They tell him it seems to happen on sunny afternoons. Clue but not a solution. The BAS already knows the outdoor temperature. He goes up to the roof to inspect the massive chiller plant, the heart of the building's cooling. Everything is perfect. The pressures are balanced, the temperatures are nominal. The computer says the system is a picture of health. But the veteran tech isn't looking at the screen. He's looking at the environment. He notices something odd. Across the street, a new skyscraper was recently completed. Its entire western face is a curtain of concave, hyper-reflective glass. A giant mirror. He puts it together. Around 3 o'clock on clear, sunny days as the Earth rotates, that massive glass facade across the street becomes a parabolic mirror. For about 90 minutes, it focuses an intense, concentrated beam of sunlight directly onto the 7th floor of his building. This solar gain is so extreme, so far beyond the design parameters of the system, that it overwhelms the cooling capacity for that specific zone. The VV boxes are commanded to open 100%, dumping in all the cold air they can get. This sudden, massive demand on the system causes a pressure drop in the chilled water loop that's so brief, the main sensors don't register it as a critical failure. But one actuator at the end of the line interprets this momentary pressure sag as a fault and locks itself closed. System error. The ghost was never a ghost. It was the sun weaponized by architecture. The solution? Not $1 million equipment upgrade. It was reprogramming the sequence of operations to anticipate this solar load and installing a few $1,000s worth of automated blinds. A computer could never have solved that. It lacked context. Couldn't look out the window. It couldn't connect a new building across the street with the fault code on the 7th floor. But a human mind, seasoned by decades of experience, could. That is the irreplaceable tool. This mental chess match, however, is only one side of the coin. The other is the stark physical reality of the dangers they face every single day. The job isn't just about being smart. It's about staying alive. The most immediate and unforgiving danger is electricity. We're not talking about the 120 volts in your wall outlet. Commercial technicians routinely work with 480 volt, 3-phase power. It's a current so powerful it doesn't just shock you. It arcs, can leap through the air. A single mistake, a moment of distraction, letting your guard down while you're troubleshooting a live panel. It's not a lesson. It's a eulogy. The protocols of lockout-tagout, of testing every single wire to ensure it's dead before you touch it, aren't just best practices. They are sacred rituals that separate a long career from a tragic headline. Then there are the refrigerants. These aren't just benign gases. They exist inside the system under immense pressure, hundreds of pounds per square inch. A ruptured line doesn't hiss. It explodes with the force of a bomb, turning copper and brass into shrapnel. The liquid refrigerant itself boils at temperatures far below freezing. A spray on exposed skin isn't a cold sensation. It's instantaneous third-degree frostbite, freezing tissue solid in a fraction of a second. Worse still is the unseen danger. In a confined space like a small windowless mechanical room, a major refrigerant leak can displace all the oxygen in the room within minutes. You don't choke, you don't gasp for air. You simply get dizzy, fall unconscious, and never wake up. It is a silent, odorless, invisible killer, and every technician who steps into a tight space has that thought in the back of their mind. They navigate a world of physical extremes. One day they're on the black tar roof of a Las Vegas casino in August, where the surface temperature hits 160 degrees, surrounded by roaring condenser fans that sound like jet engines. The next, they're on a skyscraper in Chicago in January, with a wind chill of 20 below zero, trying to get a frozen heat pump running while their fingers go numb inside their gloves. They crawl on their bellies through dusty, claustrophobic plenums filled with spiders and decades of debris, and they climb extension ladders into the cavernous darkness above a factory floor. They handle a cocktail of chemicals that can strip paint from metal. They work on cooling towers which, if not properly maintained, can become breeding grounds for Legionella bacteria, the cause of Legionnaire's disease. They are constantly navigating the razor's edge between the immense power of the machinery and the fragility of their own bodies. And through it all there's the pressure. Not the pressure in the lines, but the pressure of the job. When the cooling goes down in a hospital operating room, surgery stops. When the environmental controls fail in a pharmaceutical clean room, millions of dollars of product can be lost. When the servers in a Wall Street data center overheat, the global financial market can be impacted. The technician isn't just fixing an air conditioner. They are the person standing in the breach, the one holding back a cascade of catastrophic failures. They are the guardians of the invisible infrastructure that allows our world to function. They solve puzzles that stump computers and face dangers that would make most people run. Also, the rest of us can simply be comfortable, safe, and productive. They are the quiet professionals, the masters of an environment that everyone feels, but almost no one sees. They carry the weight of our modern world on their shoulders, in their minds, and in their tool bags. They are the reason the ghost in the machine doesn't win. But the machine is evolving. The ghost is learning new tricks. The world of commercial HVAC is not a static field of pipes and ducts. It's a dynamic, rapidly advancing technological frontier. And the technician of today is preparing for a tomorrow that looks more like something out of a science fiction movie than a repair manual from the 1980s. The next great challenge, the next evolution of this essential trade, is already here. It's happening in the code, in the cloud, and in the very chemistry of the air we breathe. Think about the concept of a smart building. It's a term we hear thrown around a lot. But what makes a building smart? It's the central nervous system, the building automation system, or BAS. And who are the neurosurgeons for this system? The commercial HVAC technicians. They are no longer just mechanics. They are becoming data scientists and network administrators who happen to carry wrenches. A modern technician might not start their day on a roof, but in front of a screen, looking at a digital twin of an entire skyscraper. They can see the real-time temperature of every single room, the airflow rate of every vent, the energy consumption of every chiller, all on a single tablet. An alarm doesn't just mean a broken part anymore. It's a data point. The system might flag an air handling unit on the 37th floor for inefficient performance. The technician dives into the data logs. They see the fan motor's amperage has been slowly creeping up over the last 3 weeks. They see the static pressure in the ductwork is higher than spec. They cross-reference this with the building's occupancy sensors, which show that part of the floor has been reconfigured into a new, high-density office space. Before they even pick up a tool, they've diagnosed the problem. The system as designed is now undersized for the new load. The ghost in this machine isn't a broken belt. It's a flaw in the logic, a mismatch between the digital brain and the physical world. The solution isn't just to fix a part, but to reprogram the system, to adjust the variable frequency drives, to rebalance the airflow, to teach the building how to handle its new reality. This is the new battlefield. It's a world of IP addresses, firmware updates, and algorithm optimization. And then there's the environmental mandate. This isn't a suggestion. It's a global imperative with the force of law. The refrigerants that have powered our world for decades are being phased out. Chemicals like R22 are long gone for new equipment, and now even its replacement, R410A, is on the chopping block. The industry is in the middle of a monumental shift towards new refrigerants, substances with names like R32 and R454B. These are classified as a 2LS, meaning they are mildly flammable. This single characteristic changes everything. Suddenly, every technician has to become a hazardous materials expert. They need new tools, new safety protocols, new training, and a new level of meticulousness. You can't just vent this stuff into the air. The fines from the Environmental Protection Agency can be financially crippling. You can't just braze a pipe like you used to. You have to purge the system with nitrogen to displace all the oxygen, preventing a potential ignition. Every single step, from recovering the old refrigerant to pressure testing the new system, is now layered with critical safety procedures. The technician isn't just protecting a client's multi-million-dollar investment. They're protecting themselves, the building's occupants, and the planet. They are on the front lines of the fight against climate change, one system at a time, handling volatile substances with a calm, practiced hand. This is a high-stakes game where a single mistake can have explosive consequences. Yet, for all this talk of data, code, and chemistry, the most important element remains unshakably human. An algorithm can't feel the subtle vibration in a compressor that signals a bearing is about to fail. A drone can't smell the faint, acrid scent of an overheating electrical contactor. Artificial intelligence cannot, and will not be able to replicate the intuition of a seasoned technician who walks into a mechanical room and just knows something is wrong. They have a sixth sense, a feel for the machine that is built from thousands of hours of hands-on experience, the echo of 1,000 rattling ducts, the memory of 100 frozen coils, the muscle memory of tightening a flare nut to the perfect torque by feel alone. This human element is the ultimate fail-safe. When the network is down, when the smart sensors are giving faulty readings, when the digital brain of the building is hopelessly confused, it's the technician who climbs the ladder. It's the technician who puts their hands on the machine, who uses their own senses, sight, sound, touch, and even smell, to find the truth. They are the analog solution in a digital world, the bridge between the theoretical and the real. So why do they do it? Why endure the brutal heat, the freezing cold, the emergency calls at 3 a.m., the immense pressure of keeping our world running? It's not just for a paycheck. For many, it's a calling. It's the profound satisfaction of being the one person who can walk into a scene of chaos and bring order. It's the quiet pride of solving a puzzle that has stumped everyone else. Imagine a hospital in the dead of a Minnesota winter. A blizzard is raging outside, and a critical component in the boiler plant fails. The building's heat is dying. Panic is setting in. The engineers are frantic. The administrators are desperate. And then the technician arrives. They walk into that roaring mechanical room, a cathedral of steel and steam, and they get to work. They diagnose, they bypass, they fabricate, they innovate, and hour by hour they wrestle that behemoth of a machine back to life. And when the first wave of life-giving heat begins to flow back through the building, no one applauds. There's no ceremony, but the technician knows. They know that in that hospital, surgeries can continue, newborns in the NICU are safe, and patients can rest. They were the one who stood in the breach. They were the one who made it work. That is a feeling of purpose that few careers can ever offer. This is the reality of the commercial HVAC technician in the United States. It is a trade that demands the mind of an engineer, the hands of a surgeon, the courage of a first responder, and the grit of a true craftsman. It is a career path that offers not just a job but a mastery. It's a field where you will never ever stop learning, where the challenges of yesterday are replaced by the technologies of tomorrow. For anyone looking for a career that is future-proof, that is intellectually stimulating, that is physically demanding, and that matters in a real, tangible way, this is it. This is a world hidden in plain sight, a profession of unsung heroes. So the next time you walk into a building, any building, a gleaming office tower, a sprawling mall, a quiet library, a bustling airport, take a moment. Feel the air. It's not just there. It's not an accident. It is the product of an incredible, invisible system, a mechanical miracle of pressure and temperature. And somewhere maintaining that miracle is a technician. They might be 100 feet up on a windswept roof, or 3 stories down in a subterranean mechanical room. They are the guardians of our environment, the masters of comfort, the keepers of the modern world. They don't just fix air conditioners or heaters. They control the conditions that allow society to function. They build and maintain the invisible empire of the air we breathe.